Titrations are just a way of applying standard stoichiometric methods into an experimental situation. And it works like this. Typically, you'll know the concentration of one solution, and you'll have another solution where you don't know the concentration. You can add small amounts of the known into the unknown until the reaction stops. And because you know the volume you've added and the concentration that you've added, you can use stoichiometry to figure out how much of the unknown was present. It's effectively a situation where both reagents are limiting reagents. The general titration follows a pattern something like this, where you find the moles of reactant A. This would be your known sample. You would have a known volume and a known concentration. And because you know the volume and the concentration, you can do some math to find the moles of that reactant. You add that until the reaction stops. Because you know the volume and concentration that were required to finish the reaction, you can calculate the moles used in the reaction. And because you stopped at the exact moment the reaction finished, you can use a mole ratio from a balanced chemical equation to get the moles of reactant B. This would be your unknown reactant. And once you know the moles of reactant B, typically you'll want to do something with it. Either find grams that were originally in the sample, or work out the original concentration of B in some solution, or something like that. But typically we don't end a problem with moles. And titrations are commonly introduced as being done with acid-base reactions, but it doesn't need to be. You can certainly do redox titrations or electrochemical titrations or any number of things. We'll use acids and bases because they're fairly straightforward. As we mentioned, titrations typically involve adding a known compound to an unknown. And the known compound is traditionally held in a piece of glassware known as a burette. And the burette is a very precise piece of equipment, and it allows you to dispense very small amounts of solution in a very controlled manner. Underneath the burette, you have some sort of flask, typically an Erlenmeyer flask, containing your unknown material. And the way titrations are usually done is you add drops of the known solution into the Erlenmeyer flask until the reaction's finished, and then you stop adding the known solution. And because the burette is graduated, you can know the exact volume that you've added into your Erlenmeyer flask, and because you know the volume you've added and you have the concentration of that known solution, you can work out the number of moles that were added, which means you can then use a mole ratio to figure out how many moles of unknown were in your Erlenmeyer flask. So we'll do an example of a titration using an acid and a base. So in our titration, we have a situation where our known compound in the burette is 0.500 molar hydrochloric acid. And in our Erlenmeyer is our unknown solution, which is an unknown concentration of calcium hydroxide, which is a base. And we know initially that there are 100 milliliters of solution in that container. And the way the titration proceeds is we're going to add acid from our burette into our Erlenmeyer flask. And we'll stop adding that acid once the reaction's done. And the way we can tell that the reaction is finished is typically by the use of some sort of colored indicator. And that indicator will change color when the reaction's complete. So in our example, our indicator would be colored pink to start with. And we begin to add our HCl, and we would add that HCl until the point where our solution changes color from pink to clear and colorless. So at the time that our reaction finishes, we can see the color changes from pink to colorless, and we've got a smaller amount of HCl in our burette. The concentration's still the same though. And the way we measure how much HCl was actually added is we take the final volume from our burette and subtract the initial volume. So this means we've added 22.17 milliliters of HCl into the calcium hydroxide solution in order to finish the reaction. And we need to work out the number of moles of HCl that represents. So we need to convert our volume to liters and multiply by the concentration of HCl. And if we use our 22.17 milliliters, convert it to liters, multiply by the concentration of HCl, we end up with a value of 0.0111 moles of HCl were added into the Erlenmeyer flask. So this was the first step in our general titration format. Find the moles that were added. Now we have to do a mole ratio to find out the number of moles of our unknown that were used up. And to do that, we need to have a balanced chemical equation. Remember that most acid-base reactions can be written as effectively just a metathesis reaction where you change the cations and anions. And once we've done that, we have to balance to make sure the number of each atom on each side is identical. So now we have our balanced chemical equation. We have the number of moles of HCl that were used, and we can calculate the number of moles of calcium hydroxide that must have been present in order for the reaction to finish. And when we do this, we find that 0.00554 moles of calcium hydroxide must have initially been present. And the final step in our standardized titration format is do something with the moles of the unknown compound. And this can vary. It really depends on what the question asks. In this example, the concentration of the calcium hydroxide initially was unknown, so we might as well figure out what that unknown concentration was. So we know that our number of moles of calcium hydroxide before we did anything was 0.00554 moles. We know that we started with 100 milliliters of calcium hydroxide solution, which is just 0.1 liters. And we can work at the concentration in molarity, which is just moles divided by liters. And we can find that the original concentration of our calcium hydroxide was 0.0554 molar.